Good morning, everyone. Just want to make sure I'm using the right microphone. Okay, so good morning, everyone, and thank you for being here today. I'm excited to be the first speaker in the speech and language session. My name is Nitsan, and today I want to talk about how working memory capacity is related to speech perception in older adults. Let's consider the situation of having a conversation with friends in a busy cafe. We all find this activity increasingly challenging as we age. What I'm interested in is finding why some individuals around this table manage to maintain good communication in these situations, whereas others struggles to do so. And indeed, difficulties understanding speech is one of the most common complaints among older adults, especially in noisy environments. And this, of course, impacting their participation in social and professional interaction, as well as their well-being, of course. A well-established finding in the literature is the existence of large variability in speech perception performance as we age. And this is true especially when listening conditions are not ideal, which is most of the time in real life. Now, for many years, the main source for this great variability was considered to be peripheral, meaning all sorts of age-related changes in the auditory system that can explain difficulties understanding speech, such as elevated hearing threshold, impaired time and frequency resolution, and so on. However, over the past 2 decades, it has become clear that although sensory factors play a major role in predicting speech comprehension, they're not the only factors influencing it. And people started looking into the role of individual differences in cognition. Components such as processing speed, inhibition, and specifically working memory were recognized as important players in speech perception. Most of the previous studies done focusing on this association between cognition and speech perception suggested that individual differences in cognitive capacity is mainly pronounced when testing speech perception using complex materials. By complex materials, I mean sentence comprehension, story comprehension, and not when we process single words. However, it's important to notice that all of these studies were using what we call offline measures for speech perception. These include, for example, asking participants to repeat what they heard and measuring their accuracy. Now, we consider this measure as an offline measure since it doesn't capture the process of spoken word recognition. Rather, it indicates the final result of successful or unsuccessful word recognition. What I want to suggest today is that using such offline measure might lead to an underestimation of the importance of cognition to speech perception. The process of spoken word recognition is known to be incremental, meaning that as we start hearing the first phonemes of a word, some optional lexical items opening up in our mental lexicon. So, for example, hearing pen would open penguin and penny and pencil, maybe even pens. Creating all of these together, creating a competition. And in order to achieve successful word recognition, one has to accumulate enough information as the word unfolds in time, inhibit the irrelevant phonological competitors, and only then the correct item can be selected. In this study, we used eye tracking as an online measure. In addition to traditional offline measure of accuracy. Using eye tracking allows us to look at the online processing as the word unfolds in time. So we can reveal, for example, what lexical alternatives were considered by the listener, and we can track this process at the millisecond level. We used the visual word paradigm. In this eye tracking paradigm, each trial consists of 4 images. And the listeners are asked to, this is how the trial looks like, and the listeners are asked to press on the image of the target spoken word they've just heard. Now, each display would consist the target word, in this example, pencil, and a phonological competitor, in this example, penguin, and 2 phonologically and semantically unrelated items, in this example, boat and computer. To make things even more complicated, we used a sequential dual task design. So prior to each trial, participants were asked to remember either 1 or 4 digits for later recall, creating what we called a working memory load. So we had 2 conditions, a low load where we asked participants to remember 1 digit, or a high load when we asked them to remember 4 digits. I'll go over a quick demonstration just so you can get a feeling of the paradigm. So this is how the setup looks like. This is the display and the listener listening to the spoken target word. And a trial would look like that. So in this example, it's a high working memory load trial. So the listener would hear, for example, try memorizing 7, 2, 4, 9. And then images would appear. And they receive 2 seconds to, this is their eyes, to scan around, to look at the images, and a fixation cross would appear to draw back their attention to the center. And at that point, the spoken target word is presented. So in this example, press on the pencil. Now we see here that penguin, the phonological competitor, was considered at some point, but eventually the participant selected the correct target word. We're interested in what happened till they clicked on the target word, what happened in the process as they heard the word. The images would disappear, and then that's the cue for the listener to recall back the digits. So a correct response would be 7249. We had 36 native Hebrew older adults listeners participating in this experiment with normal to their age hearing and normal or corrected to normal vision. And we assessed their auditory working memory span using the Wechsler digit recall to measure their maximal digit span. Based on their performance, they were divided using a median split into 2 groups of 18 participants of higher span and lower span. It's important to mention that they were all within the normal functioning span. We just divided them into higher and lower span. In case I didn't mention, the spoken instructions were presented in noise to make things even more challenging. For the results. So I'll start with the low working memory capacity group. Here we're looking at their online measure, so the online processing of the spoken word. On the y-axis, we see the proportion of fixation to the target word. And on the x-axis, we see the time from the word onset. So in general, we see that as time moves along, as the word unfolds in time, they gather more information and their looks to the target are increasing. However, when we compare their online word processing in the low and high conditions, we see no change, meaning I'm looking at the purple versus the green line, and they're identical, meaning that word processing for them was already slow, and increasing task demand, asking them to remember 4 digits instead of 1, did not change it. So increasing task difficulty had no change or had no effect on their online processing. However, if we look at their offline accuracy, counting how many words they were able to recognize, we see a significant decrease moving from 1 digit to 4 digits, so significant decrease in the word recognition, meaning they were able to recognize fewer words when asked to remember 4 digits. I'm going back to this plot, but this time we'll look at the other half of it, of the higher working memory capacity group. So same axis, same measure, but here we see that increasing task difficulty had slowed down their processing, meaning that the purple line is faster or earlier compared to the green line. When we look at their offline measure, again, I'm moving to that side of the plot, it had no effect on their performance. They were able to maintain their maximal performance. So increasing task difficulty for those listeners had no effect on their performance. I'll wrap up the results I've just presented. We'll look in general what happened when we increase task difficulty from 1 to 4 digits. Let's start with the offline measure. So for low capacity listeners, increasing task demand from 1 to 4 digits significantly decreased their performance from maximal performance to about 80% accuracy. For the high capacity listeners, for those with a higher span, it had no change. Now, the study could have stopped here, and I would conclude that the higher capacity listeners are not affected by this manipulation. However, I think that we receive a fuller picture when we take into account their eye movements, their online measure. So we see that in order to maintain this maximal performance, higher capacity listeners had paid a price or invested more effort that caused slower processing, but allowed them to maintain their maximal performance. However, for the low capacity group, they had no option to be even slower, and they paid a price in their accuracy. So I'll conclude by saying that these results suggest that adapting to adverse listening conditions is supported by cognitive reserve in a way that older listeners that have additional cognitive capacity present greater resilience to adverse listening conditions. And maybe what is happening around this table is that Mrs. Jones have higher cognitive capacity that allows her to maintain her great performance, whereas maybe Mr. Jones have a more limited capacity, and therefore he finds this situation a bit more challenging. Thank you for listening.
Okay, and thank you. We have a few minutes remaining for questions. So as Laura mentioned in the cue card and also in the chat, if you have questions for the speakers, please put them in the chat box, and the chair of that session will relay the questions to the speakers. While we're waiting for a question in the chat, I'll go ahead and ask a question. I'm wondering how the eye movements might be affected by potential ambiguities in some of the words. So for example, if the target was something that was potentially kind of ambiguous, like a bank, which could be the side of a river or a financial institution, would there be like circling eye movements around that? Or how do you think eye movements would reflect the reader dealing with the potential ambiguity of words?
So that's a great question. Actually, the target words presented today were just translated into English. We used Hebrew target words, and we made sure that we had no ambiguous words. And in addition, in our design, each pair of this target and phonological competitor, for some participants served as a target and a competitor, and then for some others, it was reversed. So some would get pencil as a target and penguin as a competitor, and others penguin and then pencil.
Okay, thank you. We have a question from Peter Pfordresher. He asks, to what extent are results interpretable based on speed accuracy trade-offs? Looks like high capacity adults were slower to fixate on target for high load conditions, while at the same time being more accurate than the low capacity participants.
That's That's an interesting question that we're actually still debating now when analyzing the results. So I'm not sure I have a straightforward answer to that. Buzz, you want to add anything on that? I see you smiling.
I'm smiling because it's an ongoing debate that we have. My feeling is the fact that we show, if you were pleased to show again the last table, Gal, if you may.
Yeah.
You can see that if we look at the eye movements, in fact, we have sort of 4 conditions. We have people who need to hold 4 digits or 1 digits, and people who have larger capacity or smaller capacity. And if you may go back to this slide, what we actually maintain is that in 3 of these 4 conditions, we see sort of the same performance. So in my view, and this is a debate between Keren Banai, who is here, Gal, and myself, in my view, if it had been only a trade-off, we wouldn't see the fact that high capacity 1 digit, we have exactly the same performance as the 1 digits or the 4 digits for the low capacity. So in other words, the low capacity are decreasing their accuracy without slowing their performance. Before, at least in my view, they have already maxed out everything they can do. They're throwing everything they have into this crazy word processing, and that's it. If it had been a strict trade-off, we should see some slowing or some change, and we see no change. As I said, in fact, high capacity 1 digit, low capacity 1 digit, low capacity 4 digit, all look very much the same in their processing, which for me it's fascinating.
Okay, good. Thank you. We need to move on to the next talk now. So if you could stop your share and the next speaker start her share. The next talk is Phoneme Discrimination Between Native Mandarin and Native English Speakers by Chen, Nunez, and Holloway. So whenever you're ready.
Hi, good morning, everyone. It's an honor to have the opportunity to address such distinguished audience. Let me introduce myself. My name is Chen. I am a grad researcher at Arizona State University, and my advisor is Dr. Nunez and Dr. Holloway. As you can see on the screen, our topic today is phoneme discrimination between native Mandarin and native English speakers. For some time, Chinese have been learning English as a second language on a large scale. Today, there are more than 81 million English speakers in China, and the number is rising rapidly. Unlike English, Mandarin is a tonal language with a very constrained phonological structure. For example, we pronounce "a" with 4 different tones, "a," 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 and each tone contains different words and different meaning, like "ma" means mom, and "ma" means horse. So, also, Mandarin is a simple syllable template, which includes vowel and tone as obligatory parts of the syllable, and the consonant and glide and a non-obligatory component. Traditionally, in Mandarin, syllables are divided into initial, final, and tone. Most features of English phonological system, such as stress and intonation patterns, are different from Mandarin's, which who are learning English. For example, there are no vowels like "a" and no consonants like "as" in Mandarin. Therefore, native Mandarin speakers have trouble distinguishing these phonemes and try to substitute those phonemes with the nearest equivalent. Phonetic differences that correlated with phonetic contrasts may exist in a native language and make the adult speaker more sensitive to the language process. However, it is difficult to distinguish phonemes that do not exist in the speaker's native language. Many studies have addressed the issue that the second language learner have difficulty distinguish non-native language phonemes. Several approaches were suggested to improve participants' ability to distinguish the non-native contrasts, thus discriminating between phonemes is the basis for sound discrimination. Discriminating phonemes is the easiest with phonemes from the native language than phonemes from the non-native language. There are several researchers showed that native Japanese speakers who have lived in an English-speaking environment or intensively trained in English showed similar but slightly lower phoneme discrimination results as native English speakers, and show much better performance compared to those Japanese who had very little or no experience with English. For 3 paired phonemes were used for current study, but paired with p as a control pair. Also, we used a paired with a and paired with s. Each pair contains a phoneme that exists in both Mandarin and English, and another phoneme that only exists in English. Also, 3 paired words: bound paired with pound, dead paired with dead, and think paired with think. All word pairs were identical except for the tested phonemes within each pair. It was further hypothesized that the native English speakers would show the highest accuracy rates in the phoneme words discrimination tasks, which contains a and th. Then the native Mandarin speakers live in China and Mandarin speakers live in English environment. Also, the native Mandarin speakers who have lived in an English environment will have greater phoneme discrimination accuracy than native Mandarin speakers who live in China in the phoneme and words discrimination tasks that contains the a and th pairing. Finally, it was hypothesized that all participants would show similar accuracy rate in discriminating phonemes and words pairs that contains the b and the p phoneme pairs. One hundred 115 participants were recruited for this study. Participants' ages are from 16 years old to 53 years old. Mean age is 22.1 years and standard deviation is 5.87 years. Specifically, there are 29 native English speakers who live in English language environment and 34 native Mandarin speakers who live in English language environment, and 53 native Mandarin speakers who live in Mandarin language environment. All participants are college students and signed consent form as approved by Arizona State University. The study was conducted during the COVID-19 pandemic, and thus the study was administered remotely through Qualtrics using participants' own equipment. The phoneme discrimination task contains of 3 groups of phonemes and 3 groups of words, as I mentioned previously. Participants randomly heard each pair of phonemes, a total of 4 times for each pair. During the auditory process, participants were asked to watch plus sign on the screen, and the 4 choice tasks were presented. Participants need to answer the questions. These 2 phonemes and words are same or not. After complete the phoneme discrimination task, participants will answer some demographic questions such as, in what country were you born? What is the primary language spoken in your home? How long have you been studying English? And how long have you been living in English environment? The results were analyzed using a two-way ANOVA, in which the mean accuracy for phoneme and word pairs discrimination changes according to the participants group. Post hoc t-tests were used to make comparison between the 3 groups to determine significant between group differences. The effect size have been calculated and reported. There was a statistical significant interaction between participants' language group mean percentage accuracy on phoneme and word pair discrimination. Native English speakers have the highest accuracy rate than native Mandarin speakers, except the word pair that and that, and native Mandarin speakers have higher accuracy rate than native Mandarin speakers who live in China for all the pairs. Then we conduct the post hoc t-test to determine significant between group differences. Post-hoc t-tests showed that native English speakers have significantly higher mean percentage correct for distinguishing between a and as than native Mandarin speakers who live in China. Native Mandarin speakers who live in an English-speaking environment also showed significantly higher mean percentage correct for distinguishing between a and as than native Mandarin speakers who live in China. For the word pair that and that, which respectively contains phonemes a and a, it was found that the native English speakers showed a strong but non-significant higher accuracy rate on distinguishing this word pair than the native Mandarin-speaking groups. The figure suggests that by increasing the number of data points, there is a strong possibility of achieving statistically significant results for this word pair. For the word pair ends, it was found that native English speakers have significantly higher accuracy rate on the paired phoneme discrimination task than native Mandarin speakers. Finally, for the phonemes pair bo and po, where both phonemes contain Mandarin and English components, it was found that both native English speakers and native Mandarin speakers who live in an English-speaking environment significantly higher mean percentage correct score for distinguishing the paired phonemes and the word pair than native Mandarin speakers who live in China. For the phonemes that exist in both English and Mandarin, such as bo and po, the native Mandarin speakers who live in an English-speaking environment and the native English speakers both performed significantly better than the native Mandarin speakers who live in China. This result failed to confirm the hypothesis. This may be because the native Mandarin speakers with greater exposure in an English-speaking environment are more adept at distinguishing phonemes within an English words and their pronunciation than those who have remained in their native non-English speaking environment. The result indicates that even though the native Mandarin speakers who live in an English speaking environment didn't perform as well on the tasks as the native English speakers, they have a significantly higher percentage correct rate on distinguishing all the phoneme pairs than the native Mandarin speakers who live in China. This supports the pair research that the non-native English speakers perform on phoneme discrimination varies with the time that they have been exposed to an English-speaking environment. The native Mandarin speakers who have longer exposure to and therefore greater experience speaking the English language and interacting in predominantly English-speaking environment and the culture are more likely to master the second language overall, as well as its phonological words and speech interaction eventually. Such individual may attain near native English-speaking language ability. The phoneme differences on the corresponding phoneme pairs and words pairs across participants groups should be consistent with the other result. However, for the pair that, the mean performance of the native English speakers was slightly lower than the international students, which is inconsistent with the result for the phoneme pairs a and a. The possible reason for this result may be a technical flaw in the audio recording of the word pair, making the pair less distinguishable, increasing the clarity of the audio recording and increasing the number of research participants' other words. Increasing the power to detect the difference would likely to resolve this issue. This study was originally planned to be conducted as a well-controlled face-to-face laboratory experiment. A potential major weakness of the study was uncontrolled external interference. Due to the COVID-19 pandemic, all the research service had to be conducted online and all the participants completed the questionnaire with their own devices and accessories. Therefore, various sound qualities could induce an unexpected performance differences within the same group. Further research will need to be conducted in a controlled laboratory environment to limit possible external interference factors, such as participants' ambient environment and auditory quality, experimental control of the experimental environment. Moreover, future research should increase in the number of research participants and the number of phonemes and the word trials per participants. Thank you very much.
Okay, thank you. I don't see a question in the chat, so I will go ahead and ask a question then. The measures that you gave seem to tap more explicit recognition of the differences between the phonemes. I'm wondering if you think you might find stronger differences or maybe better discrimination if you used an implicit measure, maybe if you looked at priming, for example, as opposed to explicit recognition.
Yes, it's a good question, but yes, but due to the COVID, we cannot do this in a laboratory environment.
Right.
So yeah, that's a major issue.
Yeah, well, it might be something to do after
Yes,
we've returned
I
to
definitely want to try
normalcy.
this. Yeah, in the future research.
Okay, thank you. It's time to move on to the next presentation then. The next presentation is entitled Say Cheese. Sensorimotor representations of vowel phonetic articulation includes orofacial muscle movements resulting in emotional sound symbolism. And it's by you and McBeath. So whenever you're ready, go ahead and take it away.
Hi, everyone. Thanks for having me here. Sorry for the really long title. Can you see my slideshow, first of all?
Yes, we see the slides.
Perfect. So the title is very long, but really what I'm trying to do in this presentation is to convince you that orofacial movements should be included in speech processing models. And I will approach and support this in 3 ways. First of all, our lab has conducted a series of experiments confirming a sound symbolic case whose effect size depend on orofacial activity. Second of all, neuroimaging findings also implicate orofacial activity in speech processing. Last but not least, we have some ongoing research showing that there is promise for orofacial signals to improve speech recognition AI. So the Gling-Glum effect is basically a confirmed through a series of findings, a sound symbolic effect where words with the E vowel sound, as in gleam, are rated as more emotionally positive than those with the vowel sound, as in glum. So we've basically conducted 5 types of experiments that confirm the sound symbolic case, and I will be talking about them in the following slides. So the first type of experiment involved having participants rate words or pseudo words. Here you're seeing an experiment where participants rate 50 pairs of E and O words that were presented individually along a scale of -5 to +5, from most negative to most positive. And indeed, we found a moderate to large effect size when you use a pair t-test to compare the rating differences between the E and A pseudo words. As you can see, we have a Cohen's d of 0.66. Next, we have participants compare 87 pairs of monosyllabic English words, which is essentially all of the E and A word pairs that you can find in English. And we placed them along a scale and had participants place a marker along the scale to indicate the more positive word. And the closer they place a marker to a word, the more positive they consider this word to be compared to the other one. Indeed, when you compare the position that participants place the marker, it is significantly more towards the E words compared to the null middle position of the scale. And we found a huge effect size of 1.03. The next type of experiment involved us doing an analysis on the Warner et al. Word database. So the Warner et al. Database includes all English words of various lengths, and all we did was just analyze the valence ratings already provided by the database for all words that included either the E or the vowel sound. So first we ran a multiple regression model with and without the vowel type. As you can see, once we introduced vowel type, a significant proportion of variance of the valence ratings were accounted for. Then we did an independent samples t-test comparing the valence ratings for E words and words. Again, we confirmed a Gleam-Glum effect, this time encompassing the entire English lexicon. Our next type of experiment involved a semantics force choice task. This is what a trial looks like. Participants are presented side by side a pair of E and O pseudo words, and then we also presented them with one very low valence meaning word and one very high valence meaning word. And these words and their valence ratings were directly taken from the Warner et al. Database. So participants had to pair each of these pseudo words up with each of these meanings. As you can see through a binomial test, surprisingly, we got a huge effect where all 50 pseudo word pairs showed responses in the predicted direction. And among them, 30 of them individually reached significance when only 2.5 pairs are expected to do so according to the type 1 error rate. So we found a huge effect where the bias was applied to almost all pseudo word pairs, significantly different from the type 1 error rate with a huge Z approximation score. The next type of task involved having participants pair the pseudo words up with pictures. So for each trial, we presented participants with a pair of pseudo words orally along the lines of, here we have zeep. We also have zup. Which one is zeep? And within that trial, participants are presented with a pair of emotional illustration, one with very high valence and the other one illustrating a very low valence illustration. And participants have to click on one of these pictures to indicate which one they think corresponds to the pseudo word, in this example, zeep. Again, we ran a binomial test showing surprisingly again that all 60 pseudo words showed response, all 64 pseudo words showed response in the predicted direction. Among them, 60 of them individually reached significance with an amazing Z approximation score of 35.5. Last but not least, we had to test whether orofacial activity was an underlying explanation. So this time we had participants do the same rate along the scale task again, but dividing these trials into 3 different blocks that were presented in random order. Right before each block starts, we have participants, we provide them with an instruction to either read the words out loud before they rate, read the words silently before they rate, or chew gum and read the words silently. So these are the 3 orofacial activity conditions. We also tested this experiment in Mandarin Pinyin and collected data from Hainan, China. What you're seeing here is that when we combine across all 3 different orofacial conditions and both languages, well, we confirmed a Gleam-Glum effect. We also confirmed a Gleam-Glum effect when you analyze each of these languages individually, again, collapsing across the 3 conditions. Last but not least, what you're seeing here for the 3 columns is the effect broken down by languages and by the 3 orofacial conditions. And as you can see, we obtain the largest effect size when participants do the congruent orofacial activity where they read words out loud. And we see the smallest effect sizes when they chew gum and read the words silently for the rating tasks. In conclusion, we find a Gleam-Glum effect that is highly robust across sensory modalities. If you recall, we both presented the pseudo words or words in written form and also orally. And then we had participants do tasks that include rate along a scale, pair with semantic meaning, and pair with pictures. So what we find is that the participants' emotional judgment of these vowel phonemes are likely universal, and this effect is moderated by orofacial activity. So in conclusion, orofacial somatosensory proprioception seems to convey both articulatory and emotional signals and should be included in speech processing models. And this argument is also supported by neuroimaging findings. First of all, we observe somatosensory and auditory interaction effects in neural activation during speech processing. Second of all, the predominant speech processing model provided by Hickok and Popel suggests that sensory motor interactions depend on word familiarity and phonological complexity, which fits our findings of the Gleam-Glum effect. So Ito and colleagues conducted an experiment where they delivered orofacial skin stretches on participants' faces as participants listened to words played through the headphone that vary along the head and had spectrum. And these stretches were delivered in 3 different conditions. The first one is 90 milliseconds before the auditory onset. Second one is simultaneous to the auditory onset, and the third one is 90 milliseconds after the auditory onset. And the participants' neural activities were recorded using EEG. Their somatosensory event-related potential and auditory event-related potential were also recorded. And their results showed that the somatosensory stimulation presented 90 milliseconds before auditory onset, which is the one that is congruent with natural speech production, leads to interaction between somatosensory and auditory event-related potentials, but this interaction was not observed in the other 2 conditions. And due to time constraints, I won't go too much into detail about the Hickok and Popel speech processing model, but you see in the article that their model does suggest a sensory motor interaction in word articulation, and that this interaction depends on word properties. The more familiar you are with saying a word and the less phonologically complex the word you are saying is, the less sensory guidance you have to rely on to do the motor control action for articulating a word. And this confirms, this is congruent with our findings with the Gleam-Glum effect, where pseudo words provide the largest effect sizes, and this might be because that our sound symbolic effect relies on this oral proprioception sensory guidance. The dependence on the sensory representation may have led to a larger Gleam-Glum effect size. In conclusion, neuroimaging literature supports the addition of orofacial movements in speech processing models in 2 ways. First of all, we observe somatosensory and auditory interactions in speech processing. And last but not least, the nature of sensory motor interactions are consistent with the pattern of our Gleam-Glum effect findings, that there is more reliance on sensory guidance in unfamiliar or pseudo words. So regarding our ongoing research, we are currently trying to improve speech recognition models or speech recognition AI using just orofacial movement signals. So basically, we're currently working on a supervised learning model that tries to differentiate and categorize E and words just by the facial movements recordings of participants reading these words out loud. And this is just data from 3 participants, so no solid conclusion, but the model was able to reach 93.6% of classification accuracy. So this really shows promise in improving speech recognition AI using orofacial signals. So maybe come back next year, see where we are at with this, this model. In conclusion, our lab has found a series of robust Gleam-Glum effects where words with the eval sound, as in Gleam, are rated as more emotionally positive than those with the vowel sound, as in Glum. neuroimaging findings also support our argument that orofacial activity should be included in speech processing models and not just the typical vocal tract activity. Last but not least, our ongoing research shows that orofacial signals do seem to have promise in improving speech recognition AI. Thank you for your attention, and I want to especially thank my mentor for waking up this early to support me in this Zoom call. Thank you.
Okay, and thank you. We have a couple questions in the chat. Hannah Schatzer says, interesting work. Would you expect a similar gleam-glum effect from watching a talker's face produce these words versus having the participants produce the words themselves?
I think that's a very good question, and our reviewers to our publications have also brought up this concern where, well, people could say any word they want with any facial activity. So that is why we're emphasizing adding orofacial activity as a component and not stating that it is the main component to comprehending or observing and understanding someone's speech behavior. Because of course the facial activity can be moderated by facial expression, but our research shows that both of them, both the articulation and emotion expression, seem to feed into facial orofacial activity. So in short, yes.
Okay, thank you. And Mike Russell asks, he says, interesting study. One thing the study makes me think is why the gleam-glum effect exists. What do you think is the advantage or benefit of the connection between phonemes and emotion? In short, why is there a connection between phonemes and emotions?
Due to time constraint, I wasn't able to describe another neuroimaging research, but there is this neural area called the IFG orb, I think inferior frontal gyrus, somewhere specifically along those lines. And that's an area that is preserved in primates and also observed in human. And that area is activated both in picking up emotional signals and in processing semantic meaning. So the gleam-glum effect and that neuroimaging finding seems to indicate some sort of evolutionary language convergence between emotions and language processing. And what that might mean is that that brain area originated as an area to process and respond to emotional signals that later in humans developed more connection with other important areas that allow for semantic processing.
Okay, and we just had another question from Monica, and I apologize if I mispronounce Ashokumar. She says, nice talk. Do you think there would be any difference in this effect between children and adults? Would experience play a role in such an effect?
That's a great question. You know, how does developmental language stages vary? So the pictorial gleam-glum study was actually developed to test it to test the gleam-glum effect on kids. That's why we only included 32 trials, taking into consideration kids' attention span. However, unfortunately, due to COVID, we were not actually able to just go to the museum and collect data like we planned to, but maybe come back next year, see where we are at that stage, because we are actively planning on testing this on kids again in the near future.
Okay, thank you. I'll throw in just one brief comment before we finish. The orofacial results were very reminiscent to me of Zions's facial feedback notions. And I'm wondering if you are sort of connecting your findings into his theory and if you think it's compatible or not.
I think I would on a behavioral level, but not on a theoretical level, because I think I'm approaching this theoretically from more of a predictive model where your motor control during articulation is facilitated by accessing sensory representations, whereas the facial feedback model has more of the emotion reliance component to it. But I definitely see a connection there. And in my publications, I do directly relate them and address the potential of explaining our findings with the facial feedback model. However, the reason why I'm more reserved on just describing this as a facial feedback model is due to all the findings that are controversial relating to the facial feedback model and replication issues.
Okay, I see. Thank you. Okay, time that we moved on to the next talk. And the next talk in the program, wearing a face mask does not impair voice recognition, has been withdrawn. Those speakers will not be here with us today. So the presentation initially scheduled for 9:15, they have agreed to go ahead and go earlier. So we'll move on to the 9:15 presentation, which is entitled Lexical Stress Perception is Influenced by Seeing a Talker's Gesture, but Not Face. And that's by Bujok, Meyer, Bosker, and my apologies if I mispronounced the name. So whenever you're ready, you can go ahead and start the next talk.
Okay, thank you very much. I think you should see my slides now.
Yes, we see your slides.
Okay, great, thanks. Yeah, so thank you very much. Thank you for having me. So yeah, I'm Ronnie Bujok from the Max Planck Institute for Psycholinguistics in Nijmegen, the Netherlands. And what I'm about to present to you is part of my PhD project, and it's titled Lexical Stress Perception is Influenced by Seeing a Talker's Gesture, but Not Face.
Yeah.
So first...
yeah, actually, it looks like we're seeing your presentation mode. So if you could go to like a full screen or something so we could see the slide a little better, a little more easily.
I think like this.
Yes, that's better. Thank you.
Okay, great. Yeah. Yeah, so first let's start with some background. So basically when I talk about lexical stress, what I mean is the emphasis of a syllable in a given word. So it's essentially the difference between object and object. And there's many different ways to express lexical stress. Most importantly, maybe fundamental frequency, duration, and amplitude. But I'm not going to go into too much detail there, because what we were interested in are the visual cues, or like the visual information of lexical stress. Because producing lexical stress can actually also lead to different articulation that is visible in a speaker's face. So Getz and McBeath have found that just presenting muted videos of a speaker's face to participants is enough for the participants to determine the position of lexical stress. In some instances, they could even distinguish between secondary and primary lexical stress. But of course, usually in normal communication, we don't just see a speaker, we also hear them, right? So the study did not test any audiovisual effects, which would be very interesting to know if this visual effect holds up in audiovisual context. Another source of visual cues associated with lexical stress are beat gestures. So basically, beat gestures are very simple flick of a hand gestures that align to stressed syllables. And Bosker and Peters have found that the alignment of a beat gesture influences the perception of lexical stress. If a beat gesture is aligned to the first syllable of a word, people are more likely to perceive lexical stress on the first syllable. However, in their experiment, they masked the face of the speaker. And considering Getz and McBeath's findings that there is actually a lot going on in the face, we were actually wondering what would happen if we took everything together, and would these visual cues influence audiovisual perception of lexical stress in a more naturalistic multimodal setting, where you see the whole speaker and you hear him. So to do that, we had two experiments. The first one that looked at facial cues, and then in the second one, we investigated manual beat gestures. So let's start with experiment one. Essentially what we did is we chose 7 Dutch lexical stress minimal pairs. Those are segmentally identical words that only differ in the placement of lexical stress. They were all disyllabic. So for example, it is the Dutch kanon, so singing canon, or kanon, which is shooting cannon. Now here SW refers to, is a short for strong weak. So a strong weak pattern is stress on the first syllable, and WS stands for weak strong, reflecting lexical stress on the second syllable. And we recorded the speaker producing all these words naturally. And then we extracted the audio and we interpolated the pitch contours, the F0 contours of both words to create a 7-step lexical stress continuum. And we made sure to keep duration and amplitude constant. So we only manipulated F0. We had 3 conditions: an audio-only condition where people heard only the lexical stress continua, the video-only condition where they would see the original video recordings, the speaker producing either the SW or WS word without hearing anything. And most importantly, we combined it to the audiovisual trials where participants would see the speaker or either video of the speaker and together with the whole lexical stress continuum. And we tested 48 participants in a 2 AFC task. And here I'm showing you a trial sequence of an audiovisual trial. Participants would first see a fixation cross, then the stimulus, which in this case is a video of a speaker, either saying canon or canon, and simultaneously presenting a step from the lexical stress continuum as the auditory signal. And then participants were asked to decide what they thought the speaker said. Moving on to the results. First, let's look at the audio-only results. So in this figure, you can see on the x-axis, that's the continuum steps, the auditory lexical stress continuum, ranging from 1 being a very clear SW pattern, so lexical stress on the first syllable, to 7 being a very clear WS pattern, so lexical stress on the second syllable. And on the y-axis, we plotted the proportion of SW responses. And as you might expect, when participants hear a clear SW, so step 1, they respond overwhelmingly with SW. And on the other hand, when they hear a clear WS, they respond more WS. And step 4, the most ambiguous step in the middle, they have a proportion of SW responses of around 50%. Now, this is what we'd expect for the audio-only condition, but we were asking, does seeing a speaker or a video of a speaker saying either SW or WS, does that bias the responses at all? And what we found is that it doesn't. In fact, as you can see here, the colored lines overlap almost perfectly with the black line, meaning that regardless of what video the participants saw, their responses were very similar to just hearing the speaker. But it's not that they couldn't see the visual cues on the face, because if I now show you another panel where we plotted the responses from the video-only condition, you can see that participants actually do see a difference. When there is no auditory signal, then participants respond more SW when they see the original video of the speaker producing SW, and they respond more WS-like when they see a video of the speaker producing the WS word. So now moving on to the second experiment, where we essentially took the first experiment and we added another variable. We added the beat gestures to it. And we got rid of all the audio only and video only trials. So we only focused on the audiovisual trials. And what we did for the stimuli was essentially we took the original videos from the first experiment, and we took the upper half of the video, so just the facial information, just the head, and we replaced that and superimposed it on videos of the speaker producing a beat gesture on either the first or the second syllable. And as you can see here, the circles, they indicate the apex of the gesture. So that is the final stop of the gesture that aligns with the onset, with the vowel onset of a given syllable, here indicated by the lines. And green shows alignment with the first syllable, orange with the second syllable. And keep in mind that this was fully crossed. So the beat gesture or the alignment of the beat gesture could indicate a different stress pattern from the facial information. And that was combined, presented with auditory lexical stress continuum. Again, we tested 48 participants in a 2 AFC task. And here are the results, or at least some of the results. Again, a very similar graph to what you saw before. here, the colored lines show the beat gesture alignment. The green line shows an alignment with the first syllable, so SW, and the orange an alignment with the second syllable, so WS. And what you can clearly see is that the green line is higher than the orange line, meaning that when the beat gesture indicates an SW pattern, people actually respond more SW-like. Whereas when the beat gesture indicates a WS pattern, people respond more WS-like. What you can also see is that if the auditory signal is very clear with regards to lexical stress, so step 1 and step 7, the effect is pretty small. But as soon as the auditory signal is ambiguous, so step 2 through 6, the effect is bigger. But now this is just the beat gestures, right? But we also had the facial information, which in the first experiment, we did not find an effect for. And in fact, here in the second experiment, we also don't find an effect. So the solid lines show the face of the speaker producing SW, and the dashed lines show WS. And as you can see, these lines, the solid and dashed lines, overlap pretty much within each beat gesture condition, indicating that the face does not affect the perception of lexical stress, whereas the beat gesture does, regardless of whatever facial information is conveying. So concluding, unimodal effects don't always generalize to more naturalistic multimodal communication. Just because there is a visual effect does not mean that it holds up in audiovisual communication. But we did find that some visual cues, specifically beat gestures, do influence audiovisual speech perception, especially when the auditory signal is ambiguous with regards to lexical stress. And the beat gestures influence the perception of lexical stress regardless of whatever the face is conveying. So taking everything together, we believe that speech perception is best considered in its natural multimodal setting. Thank you very much.
Okay, thank you. We have time for questions. Okay, there are no questions in the chat yet, so I will ask a question. I'm wondering what would happen if you dissociated more the auditory and the gestural components, maybe doing the gestural components, for example, at a different kind of tempo. What kind of effects do you think you might get?
So what do you mean with tempo specifically?
Having the person sort of speed up or kind of shift in time where the peak of the gesture would occur.
That is actually a very interesting question. I wouldn't really know what to expect then. I think that the speech rate definitely could influence our perception of the alignment of the beat gesture, and thus also the alignment of the video as a whole. But I wouldn't really know.
Okay, we have a question from Siddhar Kushanamurthy. Again, my apologies if I misspeak. Sorry. Not a question. I misread something in the chat, so my apologies.
Okay, no worries.
Do we have any other questions? Okay, yes, we have a question from Hannah Schatzer. She asked, how well did the incongruent face cues align with the audio? Was it unnatural when the stress patterns between the two were mismatched?
That's actually a very good question. So, of course, because we set the duration of each syllable to like a constant average value, like there was some misalignment, and of course, like aligning like a video from the SW with like a WS would cause some misalignment. To make sure that the alignment is not too misaligned, we decided to align it at the second syllable onset, which leads to minimal misalignment in the first and second syllable. And we also measured it, and it was something around 35 or 40 milliseconds on average, which is well within the realm of what people perceive as synchronous. And no participant reported any weird artifacts or asynchronous asynchronies.
Okay, good. Thank you. There was a clarification on what I misread in the chat a moment ago. The question is, given the facial masks that we're using in the pandemic today, do we lose some of this information?
Yeah, so it's a little bit of a bummer that the presentation that was supposed to happen before me, that we did not get to hear that, because that was it was all about the facial masks. I do believe that it takes away some of the visual information, but as the experiment 1 showed, apparently the visual information is not such a strong cue, which is surprising because it is directly linked to the production of lexical stress, whereas the beat gestures simply happen to be aligned with it. But I guess beat gestures are simply a more salient cue. You can easily perceive it in the periphery, and for the visual cues of the face to actually play a role, you really need to pay attention to them. And I think as soon as there's an auditory signal, people pay less attention, or might pay less attention to the face.
Okay, thank you. Do we have any other questions? Okay, then we will close this session. We're closing a little bit early because we did have that one talk withdrawn. However, the rest of the schedule for the day remains unchanged, so we're not going to shift anything else, which means that we'll have a break now, and the break will last until 9:45 Central.
After a year or so, and we'll begin shortly. So Laura, I guess you could kind of start sharing your screen with your talk to get us ready.
Yep, it's in the same slide. It's in the same
slide. Okay, great. So we'll go ahead and get started. Just like the last session, so I'll be monitoring the chat for your questions and reading them as best I can to the presenter. I will keep time on a timekeeping device and let people know again through the chat when there's 10 minutes left. And without further ado, let's go ahead and begin with talk number 1. So we launch headfirst into applied research, which is great. The influence of advertisement, pitch, tempo, and timbre on the perception of product features. And Laura Getz is our presenter. Take it away, Laura.
All right, hello everyone. Welcome back for the second session. It's bright and early here in San Diego, still pre 8 a.m., but I'm happy to be here today and tell you about the project that I'm talking about. Is actually my student Jordan Tran, who graduated last May. This was part of her summer undergraduate research project that she did in summer 2020 and then into the following year. So previous research has shown numerous examples of how music can affect consumer behavior. For example, there's a study where customers bought more flowers when love songs were playing as opposed to when pop music or no music were playing in a flower shop. And also evidence that people tend to buy more expensive wine when listening to classical music compared to top 40 music in a wine cellar. Beyond genre differences, specific features of music may also influence product perception and purchasing, such as the pitch of a speaker's voice or the pitch of a musical excerpt can influence the size of the advertised product. So in this Low and Hall's study, they found that a lower pitch of the voice of the speaker or lower pitch in the background music was associated with the perception of a larger advertised sandwich. Whereas a higher pitched voice or higher background music was associated with the perception of a smaller advertised sandwich. But other work in our lab, for example, suggests that there's little link between pitch and size. So we wanted to see whether we could replicate this effect. So our goal then was to replicate and extend this Low and Hall's finding relating to pitch and size. We specifically wanted to look at pitch and size, but also several other music features to see how they can affect consumers' visual imagery and of a product and therefore influence their consumer behavior based on the auditory stimuli that they're hearing. So we looked at how pitch might affect the size of an advertised sandwich, how tempo might affect the speed of advertised sneakers, and how timbre would affect the durability and weight of an advertised laptop. So we started with the replication of Lowenhall's study 1, which was the pitch of the voice, and study 2, which was the pitch of the background music. And for this first experiment, we did this as part of the Center for Open Science SCORE project. So this is Systematizing Confidence in Open Research and Evidence. And I did this in collaboration with Erin Hannon and her students, Jared and Mary from University of Nevada, Las Vegas. And as part of this replication, we did a large scale replication of this study where we had the pitch of the voice of the advertisement was either scaled up or down. And we did this with 615 people on MTurk and found that there was no main effect of voice pitch condition. So the means were very similar on a 7-point scale. It was 5.09 for a high pitch and then 5.21 for low pitch. So it was slightly higher, but not significantly higher that they rated this sandwich, with the difference in the voice of the speaker. So then we did a replication of study 2 as well, where they changed the music. So here there was no voiceover. You're just listening to the background music for the ad and asked to rate the features of the advertised product. And again, we found that the people in this case who heard the lower pitched music did not believe that the advertised laptop was any larger than those who heard the high pitched music. And also, importantly, people rated the low pitch music in this example, which was again a direct replication, as less realistic, lower quality, and more strange than the high pitched music. So we wanted to choose a different recording and see whether the same type of thing would happen. So we created 3 new advertisements. As I said, we either manipulated pitch, tempo, or timbre. So in this first experiment, people only heard one of these advertisements, either for pitch, tempo, or timbre, and then they would either hear the high pitch or low pitch, fast or slow tempo, and trombone or flute timbre. I forgot to share my sound, so I don't know if this will actually work right now. I'm not going to share the sound, but if people are interested, I can send you the sounds later. So we, again, had an advertised Cosmos Turkey Club sandwich, which is what we used for pitch. And the pitch of the music in the background was either higher or lower, and the voice was exactly the same. For tempo, we had Zoom Ride 3000 sneakers that we created an ad, and the background music was either faster or slower, again with the voice of the ad being exactly the same. And then for timbre, we had either a trombone or a flute playing the same piece of music, and there was advertising a laptop, and we were looking to see whether it would affect the weight and the durability of the laptop when it was a trombone versus a flute. So again, starting with size, we found that there was no effect of pitch on the rating of the size of the sandwich. There was also no effect of tempo on the speed that people thought that the sneakers would make you run, and no effect of timbre on the durability or the weight. So we wanted to see whether we could get this to replicate. So we wanted to make sure that people were really paying attention to the music, as opposed to it just being in the background and not having to answer any questions about it. So in the next version of the experiment, the beginning setup was exactly the same. They would hear either a high or a low pitch version of the music, the background advertising this sandwich. But then before they answered the product questions, they had to rate the musical feature of interest. So for example, in the pitch condition, they would be asked to rate the pitch of the music in the advertisement on a scale from much lower than average to much higher than average. So we could make sure that they actually noticed that it was high or low pitch in the background. And then we asked them the same questions as the previous study. But again, this didn't matter for size. We found no effective pitch on the size of the sandwich. But we did now find an effect of tempo on the speed. So people thought that you could run faster with the sneakers when it was faster music compared to slower music. And also for durability, they thought that the trombone led to a more durable laptop than a flute in the background of the advertisement. And also in this condition, participants didn't actually rate the pitch of the music as higher or lower in the conditions as we expected. So we wanted to try one more manipulation to make sure people really understood that this was high music compared to low music in making their judgments. So we did a relative comparison. So before they heard the advertisement, they heard just the music portion of it. They would hear the high pitch version and then the low pitch version. And we would ask them, was the second ad or the second music sample you heard higher or lower than the first, right? So we really knew this time that they knew that this was low music or high music. And then we gave them one of the versions of the ad to listen to. And we did the same thing for tempo. Was the second one faster or slower? And for timbre, we asked, was the second one more brass-like or more woodwind-like? And then we proceeded with the same experiment. So they would hear one of the versions of pitch, tempo, or timbre. And then before they got to the product questions, they would have to rate the musical feature. So on a scale of much lower than average to much higher than average, what was the pitch in this particular sample? So in this, we found that 8 of our participants answered the pitch question incorrectly, meaning they didn't know that the second one was higher or lower than the first. 4 people answered the tempo question incorrectly, and 8 people answered the timbre question incorrectly. And so we ran our analyses with all 56 people and with the incorrect participants excluded, and none of the effects changed. So here I'm going to report the data with only the correct participants. So these are the participants that definitely knew that this was lower or higher than the other sample. And it still didn't matter. So there's still no effect of pitch on the size of the sandwich. But again, there was an effect for speed and there was an effect for durability. And weight was also in the correct direction, but it wasn't significant in this case. So overall, we found no effect of pitch on the product perceptions, which was contrary to the Lowe and Hall's study. But we did find a significant effect of tempo and timbre on the different product perceptions. We found that faster tempo of music led to the perception that sneakers would help the wearer run faster, and that a trombone as it flows to a flute timbre would lead to the perception of a more durable laptop. And interestingly, we found that the features of music, although they can influence product perceptions, the influence was minimal if you don't really emphasize the music and ensure that participants are attending to the relevant features of the music that we wanted them to pay attention to, which could be relevant for consumer behavior because background music may not actually have that significant of a role as store owners or advertisers would like to believe, unless you're drawing people's attention to the music specifically. All right, so I just wanted to thank Ken Bates from our marketing department who helped us come up with the advertisements that we used, and my husband Adam who did the voiceovers for the advertisements. And thanks to the Lamp Lab for helping us run this study.
Thank you very much. And we do have our first question from the chat from John Newhoff. Nice work. Some work from Bruce Walker's lab has shown individual differences in polarity mapping of pitch and size. For example, some say low pitch is big, others say it is small. Might this account for your null findings in pitch versus pitch size relationships? I'm paraphrasing. Also, have you discussed informally at all the fact that Arby's uses James Earl Jones in their sandwich ads?
I did not know that specifically. So when we did the voice, we had the same speaker and we artificially manipulated their voice to be higher versus lower, which is what Lowe and Halls did as well. But yeah, so I think previous work in our lab has also shown that there's not an effect between pitch and size, or that if you ask people to pair it in the opposite direction, they can do it just as easily in the opposite direction for pitch and size. Whereas for something like pitch and elevation, they can't easily switch it the opposite direction. So I think that could definitely have something to do with it, that that if people have different mappings or the mapping isn't as strong for pitch and size, that might be why there's no effect here.
Great. And now here's a question from Michael Hall. Thanks, Laura. The spectral centroid is known to change predictably as a function of the size of an acoustic instrument. I'm thinking of Patterson's work with various sizes of string instruments. Do you intend to look at all whether differences in the centroid, a timbre characteristic, might similarly predict product size?
Yeah, I hadn't thought of other things that might predict size. Like I said, we were just starting with this replication, but that would be interesting to have other things that might relate to size, since clearly pitch and size were not as related as we thought they would be, high versus low pitch. So looking into other things that could affect size would be interesting to see if we can get some significant effect.
I have a question out of my own curiosity. So John mentioned RBs. How often do advertisers use these cues? And so I'm wondering if advertisers are sort of duped into thinking that this pitch works out, or whether this is more a creation of psychologists and acoustic.
Yeah, I don't know. I would be curious to ask my marketing colleague here how much people actually in marketing pay attention to these things, or if it's something that we think about because we're thinking about cross-modal correspondences, but maybe it doesn't actually have that application that we think as psychologists that it should.
Great. We're going to do one more question. And while we do that, Laura, would you mind unsharing your slides and the next speaker start sharing? So our last question for this talk is from Mike Russell. With respect to audiovisual commercials, do you believe your results suggest that the gender of the voiceover individual would not have an impact? Also, how do you relate your study and finding, my chat just disappeared. How do you study and finding with the studies that have shown that we are able to relate acoustic properties to physical dimensions of objects, for example, length, hardness, hollowness?
So I think that even if we can do these things, I think maybe they're not as automatic as we might believe. And so although you can correlate physical dimensions of objects like length and hardness with acoustic dimensions, my work has shown that you can also flip them the other way. So if you force people to think about it a different way, you can. And so I think that maybe these just aren't as strong as we previously believed. And if you ask people to do it a different way, they can do it because it's not as ingrained as we think.
Great. Thank you so much, Laura. And if we were all here together, we would all be applauding. So we'll now switch over to our second speaker from this session. So Chihiro, we're not seeing your there you go. Okay. So our next speaker is Chihiro Honda and a few other authors. The talk title, as you can see, is Effects of Musical and Language Background on Pitch Imitation Ability.
Great. Thank you, Peter, for the interaction. Hi, everyone. I'm Chihiro. I'm a PhD student at University of Buffalo, and I work with Dr. Peter Pfordresher. And today I'm going to present our study that investigates the effects of musical and language background on pitch imitation ability. We just finished collecting and analyzing data this week, so I'm very excited to present the result to you today. And also I would be happy to hear any feedback, suggestions, or questions if you have. Okay. First, we define vocal imitation as any attempt to match the acoustic events with voice. Vocal imitation is important, especially when you learn how to sing a song or speak a new language. In our study, we focus on the imitation of pitch because pitch is an important feature for both language and music, and also because it is comparable between two domains. The main questions we are interested in is why there are individual differences in vocal imitation ability. For example, some people are good at imitating different accents while other people are not so good at it. In the current study, we investigate the effects of long-term experience in language and music, specifically musical training and tonal language speaking experience. Past studies suggest that musical training and tonal language speaking experience may benefit auditory processing across domains. First, the opera hypothesis suggests that musical training facilitates language processing. Consistent with this hypothesis, some studies have found that musicians exhibit perceptual enhancements in language abilities, such as sensitivity to prosodic cues and lexical tone identifications. Conversely, the experience of speaking a tone language may also facilitate music perception and productions. As you may know already, tonal languages use pitch to identify words' meaning, and people who grew up speaking a tonal language are also sensitive to pitches and exhibit enhanced musical perception ability. In addition, Pfordresher and Brown found that tonal language speakers are better at imitating musical pitch than intonation language speakers. Also, long-term experience in music and language changes the way our brain processes information. This figure shows that the top-down and bottom-up processing of sound information in the brain. In the bottom-up processing, sounds travel from ear to auditory cortex through the brainstem that extract information and process sound informations. As we gain experiences such as musical training, we form top-down feedback pathways, which connects the cortex through the brainstem. And these feedback pathways help the brain detect and encode incoming sound patterns. In the current study, we investigate whether the top-down feedback pathways developed through musical and language experience affects pitch imitation abilities. We also investigate bottom-up factors related to the complexity of pitch time properties in the acoustic signal by comparing different types of sound patterns, that is Mandarin and English speech intonations and songs. Now I'm going to talk about our methods. So we recruited native English and Mandarin speakers and classified them into either musicians or non-musicians based on the years of musical training. We collected data until we had 20 participants for each group. So we have 51 English speakers and 75 Mandarin speakers, and about 30 to 40 of them had more than 3 years of musical training. We use 3 types of stimuli in order to look at the effects of long-term experience within and across domains. First, we recorded 12 sentences in English and Mandarin languages produced by native speakers and extracted pitch information from the recordings. Then we created song stimuli based on the speech stimuli by assigning a musical note to each syllable based on the extracted pitch. I'm going to play an example of the original sentence, speech, and song stimuli. Let me see if I can play this.
The children can't sleep?
So we use these phonetically neutral sounds in the experiments. Now I'm going to play an example for Mandarin stimuli.
这夏天特闷。
During the experiment, participants listened to one of these pitch sequences and imitated the sequence using their voice. We predicted more accurate imitation for a song than for speech based on the previous study that found a song advantage over speech in pitch imitation. Also, we predicted the enhanced pitch imitation ability based on long-term experience. If there is a benefit of long-term experience with music and a tonal language for pitch imitation, those with musical training and or Mandarin speaking experience would show enhanced imitation ability in both music and language domain. First, we analyze the data by using the mean pitch deviation as a measure of how accurately participants match the target pitch. In the example here, the blue line represents target and red line represents the participants' imitations. We calculated the absolute difference between the target pitch and imitation pitch for each time point, average the deviation for each trial, and then average the deviation across trials. First, we ran a full-way ANOVA with stimulus domain, stimulus language, musical background, and language background as independent variables. The x-axis represents target stimuli, and the y-axis represents mean pitch deviations. Higher value means poor imitation, and lower value means good imitations. We found a main effective stimulus language and stimulus domain, and a significant interaction between them, which indicate that the accuracy of pitch imitation was higher for song than speech in both English and Mandarin stimuli. And the song advantage was larger for English stimuli than Mandarin stimuli. We also found a main effective musical background and a significant interaction between musical training and stimulus domain. In general, musicians perform better than non-musicians. The significant interaction suggests that the benefit of musical training was larger for song imitation than speech imitations. However, in the pitch deviation analysis, we did not find any effective language background. Next, we also analyzed the data using pitch correlation as a measure of how accurately participants imitated the pitch changes within the sequence. In the left figure, the black line represents the participant's imitation and the gray line represents the target. Here you can see some of the pitch value almost match the pitch value of target. We calculated the correlation between the imitation and target by regressing the pitch values in the imitation on the corresponding pitch value in the target. In the right figure here, each dot represents the pitch value from the imitation vectors paired with the pitch value from the target vectors at the corresponding point of time. For example, the imitation with the is around 500 and the target pitch is around 700. And as you can see, the same level in the right figure as 700 in the x-axis and 500 in the y-axis. The correlation shown as a black line in the figure was calculated based on all the individual pairs of the imitation and target. We ran the same full-way ANOVA with pitch correlation as a dependent variable. This time, higher value means good imitation and lower value means poor imitations. Again, we found a significant interaction between stimulus language and stimulus domain, indicating that song advantage was larger for English stimuli than Mandarin stimuli. Also, we found a main effective language background and a significant three-way interaction of stimulus language, stimulus domain, and language background. So right now we are looking at the results for speech imitation only. The left side is English speech and the right side is Mandarin speech. The x-axis shows the language background. So in general, Mandarin speakers imitated the pitch changes better than English speakers. However, the plan comparison suggests that the Mandarin speaker did not perform English speakers for English speech imitations, but they did for Mandarin, outperform English speaker for Mandarin speech imitation. And this figure shows the results for song imitations. Again, the left side is for English stimuli, the right side is for Mandarin stimuli. For both English and Mandarin songs, Mandarin speakers outperform English speakers, which suggests that the advantage of a tonal language background for song imitations. However, in the correlation analysis, there was no effective musical background. So for the discussion, I have 3 main points. First, the imitation of song was more accurate than imitation of speech intonations, and the song advantage was larger for English stimuli than for Mandarin stimuli. This reflects the bottom-up factors in pitch processing, that is, the structural differences in stimulus domains and stimulus languages influence the pitch imitation accuracy. Second, we found that musicians matched the target pitch more accurately than non-musicians in both song and speech imitations, which suggests that top-down factors developed through musical training may facilitate the ability to process exact pitches in music and language. And finally, the Mandarin speakers imitated the pitch changes in Mandarin speech and all song sequences better than English speakers. This also reflects the top-down factors developed through long-term experience in language that benefits pitch processing in both music and language domain. Finally, I'd like to thank a research assistant at UB and University of Reading, and also the research funding. Thank you, everyone, for listening.
Thank you, Chihiro. We have a little over a minute, so probably just time for a question from the group. I'm not seeing a question from the chat yet. Oh, here we go. Is there an effect of recent, this is from Carolyn Palmer, is there an effect of recent music or language use? Like, so have you looked at how recently the participants were speaking Mandarin, how recently they were playing the piano, that kind of thing?
Good question. We have not looked at that, but that's would be very interesting measure. We have not asked participants when they took musical lessons. So for this experiment, maybe it's difficult to look at them at that. But we have some language information when they started learning Mandarin or English foreign languages, something like that. Yes.
Good. Probably we should switch over to the next talk. Of course, if you have other questions you don't have time to ask, I'm sure Chihiro would be happy to answer them. Thank you very much, Chihiro.
Thank you so much.
So now we'll go on to this talk that's presented by this Yahoo from Buffalo here. I hope I'm sharing the right screen. Am I sharing my real PowerPoint with you, or are you seeing my presenter view? The real PowerPoint? Okay, that's good. All right, and Chihiro's promised to help keep me on time. I'll also set a timer for myself. Right. So this talk really follows directly on what Chihiro just presented. And one of the centerpieces of what Chihiro just showed you was this distinct advantage for imitating vocal imitation of pitch that's presented in the song context, as opposed to vocal imitation of pitch that's from speech. And this talk is documenting a reversal of this advantage. Now, that's not to undermine any of Chihiro's results. Of course, why would I be so cruel as to do that to my own student? But rather to show an important qualification that I think tells us something that dives a little bit deeper into these differences across music and language. Chihiro's data, as long as several others that have come from my lab, show this advantage for imitating a song over speech in vocal imitations, singing tasks, speech imitation tasks, that sort of thing. And we find it in several different kinds of analyses. So Chihiro used a kind of analysis that we often use for these tasks because it involves tracking of fine-grained changes of pitch over time throughout the entire sequence. And when you have a stimulus like speech, where there's a lot of fine-grained and important deviations in fundamental frequency, we like to use this rather than, let's say, averaging across a note or averaging across a syllable. And so this kind of measure yields, salient differences like the one that I'm showing you here, which comes from an earlier study by Mantell and Pfordresher, using the pitch deviation score, higher for sentence imitation and for melody imitation. But we've also found this in more kind of traditional measures where we're, for instance, averaging the fundamental frequency across a sung note or across a spoken syllable. And we found it in traditional measures of the production of melodic intervals in singing or the difference in pitch between subsequent syllables in speech, again, averaging across syllables or averaging across notes. These results and this advantage is quite intuitive, and it jibes with our sense, and the sense that's in many publications to date, that the processing of pitch is done with greater accuracy and greater precision in the domain of music than in the domain of language. And so Ani Patel's opera hypothesis is really predicated around this idea that there's greater precision in music processing, so that if you spend many years practicing an instrument, that's going to help you in subsequent speech tasks. However, even before the data I'm going to present you today, there were some results that made me a little bit skeptical of how widespread, broad-based this advantage is. So Chihiro elegantly summarized the pitch correlation measure we use to look at how well people can track a kind of pattern of change in pitch over time. So this is sort of a fine-grained measure of relative pitch, if you will. So I don't really need to go through it again and describe you the whole measure. Here's an example of a sequence that people imitated in the earlier Mantel and Pfordresher study. And there's the imitation, if you could hear it. And this is the pitch time plot. This is the pitch correlation measure, similar to what Chihiro showed you. What I wanted to highlight you today is you can think about this pitch correlation in a kind of a global sense of the overall pattern of change in pitch across the target and the degree to which people track this change in pitch across imitation. But you can also think about these little micro patterns that exist within imitated notes, this is song, or within imitated syllables. And here we see some deviations from the overall general linear trend here. So that's kind of anticipating what I'm going to talk to you about today. More to the point, although Chihiro showed you a song advantage for imitation when using this pitch correlation measure, other studies that I've done prior to that have not shown this advantage. And in fact, several of their studies have found a null effect of song versus speech when using this pitch correlation. And I think a lot of it has to do with different kinds of stimuli, and we can talk about that later if need be. But in any case, some of these differences in the pitch correlation measure made me wonder whether there were some important differences between song and speech with respect to the importance of fluctuations in pitch within rhythmic units. So fluctuations of pitch within a sung note, fluctuations of pitch within a spoken syllable. And perhaps these fluctuations are actually more important within speech than within song, leading to the kind of cancellation of the song advantage in effects like the one I'm showing you here. So that led to the present study. And the present study is really, okay, let me advance. Okay, good. Is really not so much presenting new data, but really presenting a reanalysis of data from previous studies. And so I'm dipping into two different studies, one of which is published, one of which is in press. Both of these studies involve people imitating short spoken phrases or sung melodies using words, so not the extracted neutral pitch like what Chihiro talked to you about in her study. And in these studies, all of the sequences were segmented into notes or syllables based on phonetic information and then normalized based on the phonetic information. For Chihiro's stimuli, there was no phonetic information, so that kind of segmentation is not really possible there. And what we did is we analyzed pitch imitation based on two kind of different dimensions on which these analyses can be defined. The first is the time scale of the measure. So the kind of measures Chihiro just told you about involve analyzing the whole sequence as a unit and looking at changes in pitch across that whole sequence and taking the average of all of those pairwise deviations in pitch or the paired correlations. The new measure that I'm talking about today is a measure where we first look at performance within rhythmic units, within syllables, within notes, and then aggregating across those. So in this case, we're, for instance, looking at how well people track a pattern of pitch change within a syllable or within a sung note. So that's one dimension along which these analyses are defined. The second dimension is looking at pitch deviation, which can be thought of a measure of proximity of vocal pitch imitation, and then the pitch correlation measure I just talked to you about, which can be thought of as a measure of pattern matching. So in order to kind of get some intuitions down about this distinction between whole sequence analyses and within events analyses, here's an example from song imitation. So the plot on the left shows you a very intuitive time, pitch, aka fundamental frequency plot, showing a target in blue and the imitation of that target in red. This is actually a very accurate imitator. So the target sounds like this. And the imitation sounded like this. Right, so I would call this an accurate imitation. And that's reflected in the correlation plot that you can see over here on the right, which shows the correlation of paired F0 values across the target and imitation across time for the whole sequence. And as you see, it's a very strong, robust, positive correlation. But if we break down this correlation by individual notes, it's not quite so consistent. So within the first event, there's actually a null relationship, and you can see how that works, right? So the target kind of dips up a little bit, the imitation kind of dips down a little bit, so they kind of cancel each other out to some degree. The second event shows a strong positive correlation, but then the third event actually shows a negative correlation, and then we're back to kind of a null effect for the fourth one. So what the strong association we're seeing in correlated pitch time F0 changes in the whole sequence is not really matched when we look at individual events. So let's see if this example actually tells us something about song imitation in general. So here are some results for you using these kinds of analyses. So I'm starting with a pitch deviation analysis. So this is showing how proximal your imitated pitch is to target pitch across different, very fine-grained sampled F0 values. The plot I'm showing you here is the analysis that we've done in the past, similar to the kind of analyses Chihiro used. We're looking at pitch deviation across an entire sequence. Each dot is the average score of a participant across 48 imitated trials for song and for speech. Song and speech is manipulated within participant, all right? So we can talk about that. There's a very robust song advantage with lower deviations for song than for speech. How about when we do the same analyses, first looking within individual sung notes, within individual spoken syllables, we still get a song advantage when we look at pitch deviation scores. And when we use paired scores across song and speech to derive a song advantage score for individual participants, we get a robust advantage that we see is present for both cross-sequence timescales and then within event timescales. So in this plot I'm just showing you here, each dot is an individual person's song advantage score, so their mean difference across the imitation of speech and imitation of song. The central lines here are means surrounded by 95% confidence intervals. Important to note the zero crossing point, because that above zero means you have a song advantage. And as you can see, there's a strong song advantage for both across sequence and also within events. How about pitch correlations, though? Because that's really the thing that I was anticipating in my example before. So for pitch correlation analyses, when we do the analysis across the entire sequence, similar to what we've done in the past, similar to what Chihiro showed you, we have overall not such a strong, but an advantage for song over speech. So this difference was null within the studies that I'm talking about today, but when we aggregate across the subjects, the studies, and boost power, we do get a small song advantage. But importantly, that reverses when we look at pitch correlations within event. And when we do the song advantage scores, as I showed you before, we get a strong tendency for participants to show a negative signed song advantage score, which means a speech advantage. So in other words, participants in these samples were more effective at tracking fine-grained pitch changes within spoken syllables than fine-grained pitch changes within sung notes. Right, so that's a result. What do we make of the result? There are a couple ways we can think about this. One is to think that this result means something kind of meaningful about differences between song and speech. And that is that changes in F0 are more meaningful for speech than within song, right? They say something about our intentions, about what we're trying to convey. They're associated with phonetic deviations that are within speech. There are ways we could test this more deeply. Haven't done this yet. They're sort of difficult to do. I'm open to ideas. But for now, I want to talk about the second interpretation, which treats this result as a little bit of an artifact, which would say that basically changes in F0 are a lot bigger within syllables than they are within notes. So you notice them more when they're within syllables. Maybe you can't even hear them that well within notes. And so perhaps we're just finding something that's an artifact of the largeness of pitch changes within speech as opposed to song. So we can address that with our data. All right, so we can address that by looking at the variability of F0 values within spoken syllables versus within sung notes. And that's what's shown here. And as you can see, there's a lot larger deviations within spoken syllables than within sung notes, suggesting, hey, maybe this is an artifact. Maybe I wasted your time for the past 11 minutes talking to you about an artifact. But I don't think that's the case, which is why I'm here doing this. So here are some problems with this account. Let's say we do the same analysis across the entire event. Well, we still get a lot bigger speech pitch fluctuations than song F0 fluctuations. Yet we are getting a song advantage when we look at pitch correlations across the entire sequence. So the size, the magnitude of pitch fluctuations, F0 fluctuations, I should say, can't be the whole story. More to the point, if we do a detrending analysis and we remove the association between the difference in F0 variability within event from the variability in song advantage scores, we still get this reversal. We still get a song advantage, when we're looking at these pitch correlations across the entire sequence, and then a speech advantage when we look within. So based on this, I'm leaning toward that first explanation, that there's something more meaningful about pitch fluctuations within speech than within song. So in other words, this pitch processing advantage for music that we love to think about as musicians and is there in many different papers might be a qualified advantage. And we might want to think about how that advantage is related to timescales and is related to the role of pitch in these different domains. The underlying theoretical interest here for me is that there may be important communicative constraints on how we use pitch in song and how we use pitch in speech. The role of pitch fluctuations in communicating musical meaning may be very different than its role in communicating linguistic meaning. And so, so some future things I'd like to try and do with this. This result is look at the role of meaning, what happens when meaningfulness of speech is reduced, a language you don't know, manipulate phonetic information to vary the kind of parsing of things, and then you know, look at the role of timescale, and timescale is ambiguous in this way. So I want to wrap things up there, and I want to point out this is a very new discovery. I kind of stumbled on it, and there's a manuscript that's still under review, so the book is not closed. I'm very much open to your thoughts and suggestions. And I'd like to wrap up by giving a shout out to the collaborators of mine on the papers whose data I used in this analysis. So James Mantell and Tim Pruitt. Also thanks to National Science Foundation for some bucks to help out with this. And most importantly, thanks to all of you for your patient attention. Okay, so I am the moderator here. So I should be looking at the chat. Let's see. Okay, my timer just went up. Okay, I did well. Okay, so I guess I could read my own questions. So let's see. Oh, there's a lot. Okay, so maybe actually my timer went off, which means I'm out of time. So what do I do now? I'll take the first question. So primacy effect rules, and the later ones I'll try to answer to all of you one way or another afterwards. So Michael Hall, there are statistical problems with dichotomizing continuous variables. Oh no, wait, was this for Chihiro or was this for me? Oh, that was for Chihiro. Okay. Timothy Hubbard was the first person to ask a question for me. To what extent might pitch matching in speech be influenced by co-articulation, which presumably would not influence pitch matching in song? What about pitch matching in sung lyrics? Yeah, I think co-articulation is important. These issues of boundaries and segmentations is a thorny issue. And really, in the end, the best way to analyze these sorts of things is to try and look at vocalic segments, which would be a good next step in the analyses, I think. So thanks, Tim. And I think I should move on, right? You know, as chair of this session, it would be very, very bad form for me to monopolize things. So let's go ahead and move to the next. I'll try to respond to people privately. So the next person, Marisa Hoeschele, and several other people with hard to pronounce names until we get to the final author. Do parrots enjoy listening to rhythm? So great to have a comparative paper here. So Risa, I will turn the floor over to you and look forward to your talk.
Thank you. So can you see my PowerPoint? Okay, great. So today I'm going to be talking about the origins of music. And often when I say this, people think of historical origins. So for example, that Baroque music came before classical, came before Romantic, and so on. But what I want to talk about is something that goes a little bit deeper. So what is the root of all these cultural phenomena? And what I want to talk about is human biology. So my approach is to view humans as just one species on the planet. So it's an approach of comparative cognition. And it's kind of similar to an alien coming to Earth and being like, okay, well, there's these frogs here and ravens and elephants and pandas and humans. What's the difference between all these different creatures? And imagine the alien became interested in music, this thing that humans do, and then took some DNA from humans and created a new colony of humans on a new planet that had no idea that we existed. Would these humans create music? Would they have something like music? So I want to argue that they would, because music is something that's found around the world in all human cultures, no matter how isolated. So it seems to be something that we humans just do, kind of similar to how we just have language, regardless of interaction with other cultures. But of course, culture plays a huge role in music as well, right? So it's not part of our biology to DJ. It's not part of our biology to play the violin, but both of these abilities depend on abilities that we as humans just have. And these abilities that we as humans just have, we refer to as musicality. So these are culturally independent abilities. That's why I have this little picture of a caveman here. And the idea is that we build on musicality to create the cultural phenomenon of music. And so what I do is I actually study other animals to try and get a sense of where music comes from in humans. So this might seem a bit crazy. How can other animals inform us about musicality? So one way we can use other animals to learn something about musicality is to examine species that are related to us. So for example, looking at other primates and seeing in what ways are these animals similar or different to us, and what ways do they have musicality, and what ways do we differ, and why might that have happened? What might have happened in our evolutionary history to trigger that change? And another approach is to actually look for aspects of musicality in other species, and from there try and understand why these aspects of musicality occurred in these different species and why they might have developed something like this. So for example, I've spent a lot of time studying vocal learning animals. So these are animals that learn to produce their vocalizations by experience with other members of their species and their vocalizations. And this is a relatively rare ability in the animal kingdom. So we humans do this, of course, when we're learning language, but also when we are singing new songs, which makes it important for musicality. And also bats, songbirds, hummingbirds, marine mammals, elephants, and parrots do this. And so the question is, what do all these species have in common? And do they have other things in common that might be important and might give us clues for why we have musicality? So I'm going to give you one example from some research in my group on rhythm and what the purpose of rhythm might be. So first I want to talk about motor entrainment. So motor entrainment is the ability to move with the beat. So we hear some music, we are able to perceive where the beat is, and we're able to move in time with it. This is something that happens fairly automatically. Young children do this even before they start speaking. And it's a human universal, and until recently it was thought to be unique to humans. But 12 years ago, this study came out on Snowball the cockatoo based on YouTube. So if you haven't seen this video, I'll just show a little clip of it. So hopefully that transmitted well over Zoom, and you could hear the music and see that Snowball was moving in time with the music. So what the researchers actually did in this paper is that they went to Snowball's house and they took all his favorite songs that he liked to dance to and sped them up and slowed them down and assessed whether he was still able to accurately track the beat. And it turned out he was. So Snowball was able to track the beat and he is able to synchronize his body movements to it. And since then, it's become clear that this is an ability that parrots in general have. So they're able to synchronize with a beat in music and do it fairly spontaneously. And so a question that we had is why do the birds actually like rhythm the way we do? And if so, what can that tell us? So we wanted to know, is there something appealing about rhythm to these birds? So we use budgies, which we have in my lab, which are also a smaller parrot species that also can synchronize with the beat. So we created a place preference apparatus and we ran this study first in humans to make sure it even makes sense as a method for studying acoustic preference. And then we also ran it with the birds. And so we created 2 different apparati and they were basically the same. The main difference is the human one was a lot bigger. And so we had 2 rooms, one that had a rhythmic sound in it and one that had an arrhythmic sound in it. And which side was which was of course counterbalanced. And then we just put participants in there and saw where they spent the most time. Did they spend more time with the rhythmic sound or the arrhythmic sound as a measure of their preference? And this is what the stimuli sounded like. So this is the rhythmic sound. So you can see it's fairly straightforward beat. There were some participants that did dance to this music until they realized they were being video monitored. But then we had a randomized version of the stimulus too, where we took all the components of the sound and jittered them within a range of plus or minus 200 milliseconds. So all of the same components were played, but they just didn't have the same structure. And this is what it sounded like. So these are the results for the humans. On the y-axis here is the percent of time they spent on each of the 2 sides, the rhythmic side and the randomized side. And you can see the humans did spend more time on the rhythmic side. And we also reran the study with humans and decreased the jitter to just 100 milliseconds either way. And they still showed the same results. So we were able to replicate this. And we were also able to ask the humans, because they're humans, which sound they actually like better. And they also said they liked the rhythmic sound better. So that gave us hope that this was a good apparatus to test acoustic preference. But then when we looked at the budgie results, it looked like the budgies really didn't care about the sounds. They spent about equal time on both sides. But then we separated the results by sex, and we actually found that the female birds preferred spending time on the rhythmic side, whereas the male birds preferred spending time on the randomized side. So females are pink and males are blue here. And this kind of makes sense because budgies are sexually dimorphic in their behavior. So the male birds actually sing for the female birds. And when they do it, they perform this head bobbing display similar to what Snowball was doing in the video. So this is a video of Woody, the budgie, practicing to a piece of wood. So you can get a sense of what this looks like. So we're actually studying now whether their natural behavior, whether their song and their rhythmic displays are actually related to each other in some way. But what we did then is we created a new preference apparatus where the birds could actually choose what they wanted to listen to. So there were 3 perches and the birds could choose to sit in one of them, and whatever speaker they sat in front of, they would hear a sound from that speaker. So we had one speaker that played a rhythmic sound, one speaker that played an arrhythmic sound, and then one speaker that just didn't play anything in case they hated the sounds, that they could say, no, I'd rather hear nothing than hear these sounds. And then of course we counterbalanced which speaker was which across sessions and birds so that we could get a sense of what they liked. And here's a video of Pistachio the budgie showing us what this looked like. Okay, so here are the results. Again, on the y-axis here is the percent of time that the birds spent on the 3 perches, silent, rhythmic, and arrhythmic. And you can see that the males in blue here, they actually, if anything, spent most time on the silent perch. But yeah, they didn't seem very interested in these sounds, whereas the females spent significantly more time on the rhythmic perch than the other perches. So it did seem like our effect in the first study was driven by the female preference for rhythmic sounds. And then to look at this a little deeper, we also looked at if the birds landed on the perch, how long did they tend to stay? And while the males didn't really stay on the perch very long after landing and left pretty soon, the females actually spent quite a bit of time on the perches, especially the rhythmic ones. They would stay and listen for a long time. And you could see in that video too, that sometimes they would also vocalize back to the sound. So then what we wanted to know is, what do the females actually like about the rhythmic stimuli? So if you remember from the original sound, the rhythmic sound had a beat and metered structure, so it had a steady beat in it, but it also was repeating. So the structure kept repeating itself. So we thought, well, maybe the females just like repetition, because the arrhythmic sound was just random. So it had neither of these properties. It didn't have a beat, and it also wasn't repeating. So what we did is we created two new types of stimuli, one that had meter only, where there was a beat and metered structure, but the pattern was constantly evolving, so it didn't repeat. And then we had a repeating only version of the stimulus, where within a repetition, there wasn't really any beat structure, but then the whole crazy pattern would repeat again. Just to see what the females actually preferred. So here we tested only female budgies since the males didn't care. And here again, we have the percent of time on each perch, metered, silence, and repeating. And you can see that the females actually like both of these properties equally. So they like the metered stimulus, but they also like the repeating stimulus. So both of these factors were important for them in choosing to listen to the rhythmic stimulus. So to get back to the big picture question, how can other animals inform us about musicality? Well, one thing that it tells us is that appreciating rhythm is not unique to humans, and it may have something to do with vocal learning, and especially imitating sounds outside of our normal repertoire. So parrots, of course, are famous for imitating sounds that they normally wouldn't imitate. And to be able to do that, you have to be able to take a sound from your environment and then recreate it with your vocal apparatus. So it's just kind of a similar thing as taking a sound from the environment and moving another part of your body with it. So the two things might be related in some way. And so to answer the question, what makes us musical animals? Well, as far as we know, there's no sexual dimorphism in rhythmic behavior in humans, but having a species like budgies could be a useful model species to try and tease apart the production side and the perception side of rhythm. And there's hypotheses that suggest that rhythmic information may be used for social bonding and synchronization. And so now we can start to look at whether other species who enjoy rhythm use rhythm in similar ways to the way we do. So I hope this was an informative way of looking at humans as just one of the species on the planet. And if you want to see more of this type of thing, you can see my students' poster number 18, Bernhard, on a study about octave equivalence. Thank you.
Great, excellently timed. Thank you so much. We have a couple questions. So I'll start with the first one from Mike Russell, which is a clarification question. Did landing on the perch trigger the sound, or were the three sounds played simultaneously?
Landing on the perch actually triggered the sound. So there was an infrared beam on each perch. And so the program would notice when the bird landed and only start playing the sound at that point. So if they weren't on any perch, it was also silent. So the fact that the males didn't stay anywhere also means that they experienced more silence that way too.
Good. And our second question is also from Mike Russell. What do you think would happen if you did the same experiment with human participants?
We're actually going to do that. And we didn't do it because of COVID, of course, because we wanted to do it in person so that the humans actually have to stand in front of, we have an apparatus set up, and the humans can stand in different places in a room, and depending on where they stand, they trigger different sounds so that we can make it comparative, because there's been cases, right, where you ask humans what they prefer and they say something different than what they would actually do if they're investigating a space, because sometimes we stay and listen to a sound, not maybe because we prefer it, but because we're curious about it. And so the definition of preference and what that really means gets a bit complicated. So it's important when we do these comparative studies that we do the same procedure in the humans. But yeah, that's definitely planned. The apparatus is ready and we'll do it soon, I hope.
Good. We have two more questions, but I'm afraid we only have time for the first of the two. So the second one, maybe you can answer offline. So the first one's from Carolyn Palmer. Can you clarify again why it makes sense that the females and not males would be more sensitive to the rhythm? Seems counterintuitive based on who usually presents the song.
Yeah, so I think the two sides are separated, right? So the males are the ones that produce the rhythms and the females are the ones that are the perceivers of the rhythms, right? So the males perform for the females and the females choose the males based on their performance. So it could be that a male would find hearing rhythmic sounds like kind of competition and not enjoyable, right? So I think maybe in the case of Snowball and other pets where they're actually interacting with music, it might have something to do with, it's just maybe a way for them to perform rather than that they're enjoying listening to the sound. It's more of a medium for them to perform. Because sometimes also animals will perform together to create rhythms. So it would be interesting to follow up with this. And we are looking at whether the males actually use rhythm in their vocalizations along with the movements they do, and whether the movements are kind of like beat gestures that we heard about earlier in their patterns. But yeah, I don't really know, but that's what I have to say for now.
Thanks so much. There's clearly a lot of interesting questions from this. So we have to move on now to our last presentation for this session. So Marissa, if you could stop sharing your screen. Yep. And then Samantha, if you could share your screen. So our last but not least talk in the session, exploring the relation between musical and dance sophistication on musical groove perception, being presented by Samantha O'Connell, which was part of a larger team of scholars you can see there. And Samantha, go for it.
Thank you. And thanks for the APCAM team for having me today. I'm going to be actually presenting some work when I was at UNLV finishing up my dissertation, so I'm really excited to talk about it. This is the brief roadmap I'll be taking today. Brief background, some results. I'm looking at 3 different regressions on musical sophistication, dance sophistication, and musical skills, followed by some conclusions and implications. So for those of you who don't know, musical groove has been defined as a certain quality of music that makes us want to move along to it. That's been popularized by some of the artists depicted here, such as Michael Jackson, James Brown, and more recently, Bruno Mars. This type of music you may hear when you're attending a live concert wanting to dance around, when you're at your best friend's wedding at the reception, when you're cruising down what we call here in California, the PCH with your best friend in the car. You'll see a lot of kids enjoy music to groove as well as older adults. You'll also oftentimes hear it as the opening soundtrack to your favorite dance movie. And then sometimes you might feel so compelled to dance in your underwear along to music with groove or to your favorite Fortnite character. There have been some auditory characteristics that have been found in songs with groove that have been pretty similar across different types of songs with groove. Some of those being a salient beat, oftentimes played by a deep sounding instrument like the bass or drums. Oftentimes music with groove has a somewhat upbeat tempo closer to the sound of a heartbeat. Most songs with groove have some sort of syncopation, but not so much that you don't hear the salient beat being covered up. And then oftentimes songs with groove have that really killer melody that you can't get out of your head. And then some harmony, but just enough to make it interesting, but not so much that you can't hear that melody through everything else. What we've also been exploring here in our lab is that taste and familiarity can also impact the way that we hear the groove. So this is some data from Peter Janata's group from his paper in 2012, where they found that those who found songs to be more enjoyable and more familiar also found those songs to be more groovy. This could be due to a number of factors, including being a musician and having experience playing those songs could make you be able to hear different types of groove, as well as having an experience of moving along to that sort of music that could also impact the way that you hear differentiations in groove. What we haven't really explored as a community is this idea of the impact of dance experience on musical groove and whether having formal dance experience can impact the way that we hear high groove versus low groove music. So in the work that I did, we explored which musical and dance related factors are predictive of musical groove perception. Are they things like musical skills, where if you're better at tapping your foot along to the beat, or if you're better at matching your pitch to the singer? Are you better at hearing differences between high and low groove music? Does it depend on whether you have formal music training, or maybe you're a really active listener? Or possibly does it depend on the fact that you have formal dance training, you're a frequent dance spectator or social dancer? So we collected data from 124 participants at UNLV. This was entirely an online study due to the COVID-19 pandemic that has impacted all of research. This was done over headphones on a computer or laptop and took about an hour to an hour and 15 minutes to complete. You can see here on the left is all of our demographics information, and we had a range of people who had lots of music and dance experience all the way to people who did not have any, and a lot of variation in years of practice and weekly practice hours. I did a number of different tasks with my participants, the first being a musical groove judgment task where I had 10 high groove and 10 low groove songs, and they were asked to just rate the songs. How groovy were they on a scale from 1 to 7? I then took the mean of the high groove and mean of the low groove music scores, and I created what I called a musical groove difference score that indicated the biggest or smallest difference between those two groups of songs. I also administered a couple of self-report tasks, one of them being the Goldsmith Music Sophistication Index from the Mullen-Seethan group. Here they measure overall musical aptitude that doesn't necessarily link to formal music training. So you can see here it's based on 5 factors: music training, singing abilities, emotions, engagement, and perceptual abilities. What's also really cool about this work is that the same group came out with a dance sophistication index about a year ago that mimics the way that the music sophistication index was designed, where there were 5 factors about dance aptitude that weren't necessarily based on formal dance training. So here you'll see those 5 factors are body awareness, social dancing, urge to dance, dance training, and observational dance experience. I also administered a couple of more objective tests that measure those musical skills I talked about earlier. This is a subset of tests from the profile of music perception skills, or the PROMs. Participants got 2 reference clips and then were given a comparison clip and then asked whether the comparison was the same or different to the first 2 clips. So you can see here I measured skills based on melody, rhythm, accent, and tempo, and then one that's called rhythm to melody, where you're given a rhythm and then a melody to see if that melody has the same rhythm as the rhythm you were given prior. And then finally, I administered a task that was actually developed by a fellow colleague of mine and an author here, Jessica Nave-Blodgett, which is a beat and meter sensitivity task. So if some of you are familiar with the Everson beat alignment task, it's similar, except that we also added a meter level tracking here as well. So participants were given dance songs in 4/4 and dance songs in 3/4, along with a click track that either matched on the beat and meter level, just on the beat level, or just on the meter level. And there were 5 different conditions. And they were just asked, how well does that click track match the music on a scale from 1 to 4? So given all of those tasks, I generated 3 regressions. The first, I took the 5 factors from the Goldsmith Musical Sophistication Index and asked if those 5 factors were predictive of the difference that people heard between high groove and low groove music. And what I found was my overall model was significant and predicted 16.4% of the variance of musical groove difference score. And that of these factors, 2 of these predictors were significant, and that was perceptual abilities and music training. Now, of these factors, we felt that perceptual abilities was really the more significant factor. With this in mind, While musical training and musical perceptual abilities are related in our study, when they are related to musical group difference score, we're seeing perceptual abilities does have a significant relationship, and musical training does not. And our takeaway from this was that these perceptual abilities that are predictive of musical group difference score may not be those honed necessarily from music training, but could be honed from other skills, such as maybe being a bilingual listener or being in sound environments in which you are really honing those perceptual skills that aren't based in music. In our second regression, we looked at these 5 factors generated from the Goldsmith Dance Sophistication Index and regressed those to see whether those were predictive of musical group difference score. What we found was the overall model here was also significant and predicted 8.9% of the variance. And the predictor here that was significant was body awareness. And we interpreted this in a couple different ways. So body awareness, and these were all self-report measures, but those who felt that they had more body awareness may be people who felt like they were more coordinated. So we can see here that musical group difference score and body awareness were significantly related. And that could be because those who had more dance training or scored higher on the dance training factor and the Goldsmith and Dance Sophistication Index, which is somewhat related to years of dance training, that is related to how much they felt like they had body awareness. Now, what we do see here is that dance training itself did not significantly relate to musical group difference score, which could possibly mean that those who felt more coordinated may have developed those coordination skills from things like being an athlete or from being a gamer or other factors that aren't necessarily related to honing them through dance training. What we do also see here is that social dancing did have a relationship with musical group difference score, indicating that more experience you have social dancing can relate to being able to hear differences between high and low group music better. And that could be a factor of having more confidence in movement or having more familiarity with movement to groove. So that goes along the lines of taste and familiarity, where if you are more aware of groove, you might be able to hear it more. And in our final regression, we looked at the scores from the 5 proms measures that I used, along with the beat and sensitivity measure from the BMS, and we regressed those to see if those were predictive of musical group difference score. And while we predicted here that things like beat, which is really important to the feeling of the groove, or rhythm would be significant predictors, we actually didn't find a predictive regression at all here. The model wasn't significant and none of our predictors were significant, which was pretty interesting. And that's something that we're hoping to explore in the future. So the conclusions we drew here when asking the best predictors of musical groove perception that were music and dance related, we found that perceptual abilities and music training in relation to music sophistication and body awareness and dance sophistication were both predictors of musical groove difference score, but we didn't see any significant predictors when it came to measuring more objective musical skills. And our overall takeaway is that this experience of groove may be holistic and not necessarily dependent on the way the music is written or performed, but shaped by individual listeners' experiences and possibly their innate abilities. And so future directions, I now work with hearing impaired populations at USC, and cochlear implant patients are a cool group to study because they have superior rhythm perception, but not a superior pitch perception. So that can help us disentangle these important aspects of groove that make it really fun to listen to. I also would love to do work on development, especially with kids who don't have as many life experiences, to see if they hear groove in a similar way. And then also looking at more deeply with dance training, and does formal dance training help hone some of those skills that are important for musical group perception? I'd like to thank my authors on the left, the Auditory Cognitive Neuroscience Lab, past and present members, and the UNLV Grad College for helping to fund my study in my last 2 years at UNLV. And then I'm happy to take any questions.
Great, thanks. We have some time for questions. All right, to kick things off, I guess I'd like to ask you, you mentioned the issue of doing this study online via COVID, right? And it's something that a lot of us have had to deal with, and it figures into our research programs to different amounts. So in what ways did this project, would this project have been different if you were able to do it in person from what you just presented to us now?
Yes, actually. So something I was really interested in, and when I was, preparing my dissertation work, I was reading into a lot of beat production tasks. So tapping along to a beat, and I think that would answer some really interesting questions, because listening to groove is something that really makes you want to move along to it. But unfortunately, with the online format and with bandwidth and some things like that, it can be really difficult to do a really precise tapping task online and be sure that, my reaction times were all accurate. So if I could have done it in person, I would have collected beat production measures and looked at reaction times to see some interesting things about how those would predict musical group difference score.
Yeah, good. Actually, I had a second question. And so I'm sorry if I missed it. Being one of the problems with being a chair of the session is that you were so distracted by timekeeping that sometimes you miss bits of the talk. So, so I'm wondering about the way in which your measures can inform us about beat deafness and the origins of beat deafness and the potential treatments, interventions for beat deafness. I don't know whether you had a certain whether in measures you can kind of predict who might have this problem?
Yeah, that's an interesting question, and not really something I had thought of until now. I think that the beat and meter sensitivity test that Jessica developed is really cool, because it can look at beat and meter level, and it could be possible that some people who have beat deafness really have beat deafness, but can maybe hear more hierarchical information, maybe not. But something like that, where you're tapping along to a beat or listening along to a beat, could maybe, if you're really bad at that task, that could indicate you may have beat deafness. My hope, long term, is that just listening to songs with groove, which really do have a really salient beat, could be some sort of therapeutic treatment to be able to hear that beat more. So maybe you can combat some of these beat deafness issues that people have, which could be really cool.
Yeah, good. And I guess related to that, Tim Hubbard has asked, is there a groovia similar to amusia or aphasia? Might your methods address this?
I don't know, and I think I'm okay to say that. I haven't heard of it. If someone wants to give me someone that doesn't understand the groove, that would be great. I'm sure there is, in the same way that there is an A whatever of a lot of other hearing deficits, but I think some interesting ways to look at groove, and there's a lot of I talked about this with my fellow authors about groove oftentimes is looked at something that's universal, but we also look at a lot of research in this world, research world, from the Western kind of eye, and looking at maybe Eastern music, and especially music that's not necessarily in these metrical times that we're used to, and a lot of what groove is composed in, that looking at this work cross-culturally may start to maybe understand some of these questions of maybe there is a groovia or not. I really like that term, though.
Well, good. I'm afraid that's all the time we have for now, because our poster presenters have to start set up for what will be a very groovy poster session. And so I look